Here we've set up a mass spring system, so we have two springs here that are suspended from a fixed point, and we've got a mass hung from the bottom. And what we're going to do is we're going to give the mass a small displacement from equilibrium, and that will cause it to oscillate up and down with simple harmonic motion. In order to measure the period of these oscillations, we set up a fiducial mark. So you can see here the pencil has been attached to the stand just to make a marking point at the equilibrium position in the middle of the oscillation. And now if we give it an initial downward displacement, allow it to oscillate. To begin with, we can just get used to watching the oscillations for a while, and then we're going to count ourselves into the first oscillation and measure the period. So here we go. We're going to measure start as it goes down through the center of an oscillation, so -3, -2, -1, start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And there you go, count the oscillations. So for a mass spring system, once we determine the period, well, we can determine the period if we know the mass and the spring constant. So the relationship there is T equals 2 pi square root m over k, where m is the mass that we've suspended on the end of our spring in kilograms, and k is the spring constant, or sometimes call it the force constant of the spring, which will be measured in newtons per meter. And that can easily be determined if you measure the force needed to cause a certain extension in the spring, and then just F equals K delta L. F is the force, delta L is the extension, K is the spring constant. So that's very easily determined. Of course, we can plot a graph. So basically, let's say we've measured the period for different masses on the end of the spring. If we plot a graph of period in seconds against square root of the mass in kilograms, what we will get is a straight line graph that will pass through the origin. Alternatively, if we square both sides of the formula, we could plot t squared against m, and again we'd have a constant gradient. The graph would be a straight line that would pass through the origin. It's important we understand what the gradient of these graphs is going to represent. So if we compare the equation to the general equation of a straight line graph, which is y equals mx plus c, we can rewrite t equals 2 pi square root m over k as 2 pi over the square root of k times the square root of m. And if we do it in that form, it's very easy to see that if we plot t on the vertical y-axis and we plot the square root of the mass as on the horizontal axis as our x variable, then the gradient is just going to be, of course, whatever is multiplying our x variable. So in this case, it will be 2 pi over the square root of k. If we plot the graph as t squared against m, well, again, we can write the formula in the form y equals mx plus c, and if we do that, we can very easily see that in this case the gradient will be 4 pi squared over k. So if you work out the gradient, you can easily determine the spring constant from the gradient of that graph. Okay, so let's sort of look at an example question involving the mass spring system. So here, let's suppose we've got a spring suspended from a fixed point, similar to what we've just seen. We put a 300 gram mass on the end of the spring, and when we do that, the spring extends 5.4 centimeters down to its equilibrium position. We then give the spring a further displacement of 2 centimeters and release it. It performs simple harmonic motion. Can we find the maximum speed of the mass during those oscillations? Well, we know a formula for maximum speed of simple harmonic motion, and that is that Vmax is 2 pi Fa. So if we multiply 2 pi, frequency is 1 over period, by the amplitude, so we're extending it 2 centimeters, 2 times 10 to the minus 2 of a meter, we could determine Vmax. The problem is we don't know the period at the moment, but of course for a mass spring system we can work out the period using t equals 2 pi square root m over k. So if I know I've got a mass of 0.3 kilograms, of course we don't know the spring constant, but we do know that initially when we put 300 grams on the end of the spring, it extended 5.4 centimeters to reach an equilibrium position where the weight pulling the spring downwards was matched by the tension in the spring. So what we can do then is use the formula F equals K delta L, Hooke's law basically. And if we do that, we can put the weight of the mass in as the force that's causing the spring to extend. We know that that weight extends the spring by 5.4 centimeters, or 5.4 times 10 to the minus 2 of a meter. And it is then simply a case of rearranging the formula to work out the spring constant. Now, of course, once we've worked out the spring constant, all we need to do then is to place that in the formula. So we can put that into our formula. So T now equals 2 pi square root 0.3 over 54.5 Newton per meter, our spring constant. And if you put that in your calculator, you can work out a period which will come to be 0.466 seconds. Now, of course, once we've got that period, we know the period of the oscillations, we can work out the frequency. We already know the amplitude. Okay, we're giving the spring a further displacement of 2 times 10 to the minus 2 meter to set it into oscillations. And therefore, we can determine Vmax, 2 pi times 1 over 0.466 times 2 times 10 to the minus 2 will equal 0.27 meters per second. And there we go. Okay, we've got another question here which refers to a bungee jump. So it says the two diagrams in figure 4 show the student before and after making a bungee jump. So she jumps off the bridge on the end of this bungee cord, and it says here the bungee cord has got an unstretched length of 25 meters. It's fixed to the top of the railing, and the other end is attached to her waist. She's 58 kilograms. She jumps off the bungee cord. The bungee cord will go into tension at point P, and she will then come to rest momentarily at point R, and will then oscillate about point Q. Okay, so let's just think about that. Basically, at point P, the bungee rope is going to go under tension. Obviously, she's been falling off the bridge, so she'll be have a speed at that point. So she'll be travelling down quite quickly. Basically, as the bungee rope stretches, we're going to have a conversion of gravitational potential energy and kinetic energy into elastic potential energy as she drops. Point Q is going to be the center point of the oscillation. What she will do then is further extend the bungee jump to point R. Q to R will be the amplitude of her oscillation, and then she'll oscillate, come back up again, and rise just somewhere above point P. Assuming that the center of mass of the student has fallen through a vertical distance of 25 meters when she reaches point P, calculate her speed at P. You may assume that air resistance is negligible. So that's going to be a fairly straightforward question, really. It's just conservation of energy. As she's been falling from the bridge, she's been losing gravitational potential energy, and she's been gaining kinetic energy. We know GPE is mg delta h at the Earth's surface. Kinetic energy is half mv squared. We can equate those two. Of course, the mass will just cancel out. We can put in the values. Cancel the mass, rearrange the formula, and we will work out her speed, point P, and that comes to 22.1 meters per second. The bungee cord behaves like a spring of spring constant 54 Newton per meter. Calculate the distance d from P to Q, assuming the cord obeys Hooke's law. What we know is that Q is the point at which she oscillates about. It's the centre of her oscillation. And therefore at point Q, the forces are going to be balanced. The tension in the bungee cord acting upwards will equal the weight acting downwards. So we can just use F equals K delta L. Basically, we're working out the spring constant here. Or we've got the spring constant. We're working out the extension. And essentially, it's the extension in the spring that will cause the tension in the spring to equal her weight, because we're looking at the equilibrium position of the simple harmonic motion where we know the forces are going to be balanced. So to do that, F equals K delta L, put the numbers in, we can rearrange it. It comes out as 10.5 meters. We'll round it to 2 significant figures, which is an appropriate number of significant figures here, and it's 11 meters. The arrangement can be assumed to be act as a mass spring system. Calculate the time for 1/2 of an oscillation. Well, we know how to calculate the time of an oscillation for a mass spring system. T equals 2 pi square root m over k. The formula's in our data book. We know the mass, we know the spring constant. We've been given that earlier in the question. Again, it's just a case of putting the numbers in, and we will work out a value for the period. And the period comes to 6.51 seconds. So if we halve that, because it's asked us for half the period, 1/2 of an oscillation, it's 3.3 seconds to 2 significant figures. Now this next question is an interesting one. Use your answers from parts A and B part 1 to show that the amplitude A, which is the distance from Q to R, is about 25 meters. So we need to think about what we know and what's happening here. The student is oscillating about point Q. So in the first sort of quarter period they move down from Q to R, and then as they go back up, they're going to oscillate then an equal distance above Q, which is going to take them back up above point P, and that will be that will be the oscillation. So what we can use here is the formula for speed at any point in the oscillation, because we know the speed that she would have at point P. We've worked that out in A part 1. We know the displacement at point P, and we know the period, so we can work out the frequency of the oscillations. So we can use that formula basically to work out the amplitude, because we know everything else. So it's just realizing that essentially P is not the end of an oscillation, it's not the top of the oscillation, she will oscillate above that. Okay, P, distance Q to P is less than the amplitude of the oscillation. So essentially as she goes down from Q to R, she's converting, well, kinetic and gravitational potential energy into elastic potential energy, and then as the bungee cord contracts again, pulls her back up, she's converting that elastic potential energy back into gravitational potential energy, well, and kinetic energy at Q, but then that's all going back to gravitational potential energy as she reaches the top of her bungee jump. And there we go. So we can put the numbers into the equation. The question then is just rearranging it. So we've got 22.1 equals 2 pi over 6.51 times the square root of a squared minus 10.5. That should be 10.5 squared there. Just add that in. And then it's a case of just rearranging that equation. So we can times through by 6.51, divide by 2 pi, square both sides. We come out with 524 equals a squared minus 10.5 squared. So then a squared is going to be the square root of 525 plus 10.5 squared. So there we go, we'll work that out. And we come to 25.2 meters. So just to make that clear, as the student dropped from point Q, went down to point R, that's the amplitude of the oscillation, and then what they would have done is they would oscillate it on the way back up, come back above P, back down to Q. That's one oscillation. So you can see basically we know from part A that always at point P she's going to have a speed of 22.1 meter per second if the amplitude of the oscillation stays the same. We were able to use the knowledge of that along with the distance of P to Q to basically determine the amplitude of the oscillations.